A warm greetings to one and all. In this session, let's learn about random variables and density functions. In real life, most of our observations are in the form of numerical data. Those observed values are called as random variables. There are two types of random variables. First comes discrete random variable. This can be assumed only a countable number of values. Examples are number of students in a classroom. The values can be 0, 1, 2, 3, up to 30 and so on. Number of cars sold by a dealership in a month. The possible values are 0, 1, 2, 3, up to 100 and so on. Number of books on a shelf. The possible values can be 0, 1, 2, 3, up to 50 and so on. Next comes continuous random variable. It can take on any of the countless number of values in an interval. The examples are height of the student. It can be ranged as 100.5 centimeter, 150.2 centimeter, and so on. Time taken to run a marathon. The value can be 2.5 hours, 3.75 hours, and so on. Next, temperature in a city on a given day. The values can be ranged within 20.1 degrees Celsius, 25.4 degrees Celsius, and so on. Next, we can see in detail about the discrete random variables. The expression P of A denotes the probability that the event A is true. For example, A might be the logical expression, that is, it will rain tomorrow. We require that 0 less than or equivalent to P of A, that is less than or equivalent to 1, where P of A is equal to 0 means the event definitely will not happen. P of A is equal to 1 means the event definitely will happen. So here the probability values always lies between 0 and 1. That's why we have given the formula 0 less than or equal to P of A less than or equal to 1. Next, we can write probability of A inverse to denote the probability of an event not of A. So this is defined to probability of A inverse is equal to 1 minus probability of A. We will often write A is equal to 1 to mean the event A is true and A is equal to 0 to mean the event A is false. We can extend the notation of binary events by defining the discrete random variable x, which can take on any value from a finite or countably infinite set x. We denote the probability of an event that capital X is equal to small x by P of capital X is equal to x, or just P of x for short. Here P of x is called a probability mass function or PMF. This satisfies the property 0 less than or equivalent to P of x less than or equivalent to 1 and small x belongs to capital X, where P of x is equal to 1. Let's have an example here by considering the PMF defined on the finite state space X, where the value of X as 1, 2, 3, and 4. So let's consider the figure A, where we have uniform distribution of P of X, which is equal to 1 by 4. That is, we have fixed all the values here. That is 1, 2, 3, and 4. All the values have been uniformly distributed here. In figure B, we can find that we have degenerate distribution, that is, probability of x is equal to I, where x is equal to 1 always. So whenever we choose this distribution, we have to select only 1. We no need to select 2, 3, and 4. It means that we are constantly selecting the value 1, where I of is the binary indicator function. This distribution represents the fact that x is always equivalent to the value 1, as we have seen in this figure. In other words, it is constant, since we are not using 2, 3, and 4 values in the state space. Let's learn about continuous random variable. Continuous random variable x, which can take on any value within a continuous range, such as any real number within an interval a, b. We denote the probability that x falls within a specific interval a, b using probability density function. Here, f of x is called probability density function. The properties are f of x greater than or equivalent to 0 for all x. Probability of a less than or equivalent to x less than or equivalent to b is equivalent to integral minus infinity to infinity f of x dx is equal to 1. This graph shows the probability density function PDF, where f of x represents the density at each point, and the shaded area between A and B, that is, P of A less than or equal to x less than or equal to B, represents the probability that the random variable x lies within the interval. Now let's have an example problem. To predict the probability that house price falls between 50 lakhs and 75 lakhs using the probability density function. So you need a specific model for house price prediction. So that is probability of 50 lakhs less than x less than 75 lakhs, which is equivalent to integral 50 lakhs to 75 lakhs f of x dx is equal to 1. So here we have the normal distribution of house price prediction in this image. So we can see here this blue line represents the normal distribution of the house price prediction values, where the red line represents the 50 lakhs. That is, the value of the house starts with 50 lakhs, and the green line represents the value of house ends with 75 lakhs. So this shaded part represents the house price predictions between 50 lakhs and 75 lakhs. So hope you're clear on this diagram. Let's learn about cumulative distribution function. Here, discrete and continuous random variables can have cumulative distribution function CDF. The cumulative distribution function or CDF of a random variable x is denoted by f of x, and it is defined by f of x is equal to p of capital X less than or equal to small x for all x. Probability of A less than capital X less than or equal to B, which is equivalent to probability of B minus probability of A. The CDF is defined as f of x is equivalent to integral minus infinity to infinity f of y dy is equal to 1. The properties of CDF are: a function f of x is a CDF if and only if the following three conditions hold. First, monotonicity. If x less than or y, then f of x is less than or equal to y. Next, limiting values. Limit x tends to minus infinity, f of x is equal to 0, and if limit x tends to plus infinity, f of x is equal to 1. Right continuity. The CDF f of x is right continuous, meaning limit x tends to x naught plus f of x is equal to f of x naught for any point in x naught. There are no jumps when approaching from the right. So hope you are clear in cumulative distribution function. Thank you all.